Example 4. For what values of p is the integral from 1 to infinity of 1 over x to the power p dx convergent? Solution. We know from example 1 that if p equals 1, then the integral is divergent. So let's assume that p not equal to 1. Then the integral from 1 to infinity of 1 over x to the power p dx equals the limit as t approaches infinity of the integral from 1 to t x to the power negative p dx equals the limit as t approaches infinity of x to the power negative p plus 1 over negative p plus 1 on the interval from x equals 1 to x equals t, equals the limit as t approaches infinity of 1 over 1 minus p, open bracket, 1 over t to the power p minus 1 close bracket. If p is greater than 1, then p less than 1 is greater than 1. So as t approaches infinity, t to the power p minus 1 approaches infinity, and 1 over t to the power p minus 1 approaches 0. Therefore, the integral from 1 to infinity of 1 over x to the power p dx equals 1 over p minus 1 if p is greater than 1. And so the interval converges. But if p is less than 1, then p minus 1 is less than 0. And so 1 over t to the power p minus 1 equals t to the power 1 minus p approaches infinity as t approaches infinity. And the integral diverges. We summarize the result of example 4 for future reference. Equation 2, the integral from 1 to infinity of 1 over x to the power p dx is convergent if p is greater than 0 and divergent if p is less than or equal to 1. Type 2 discontinuous integrands. Suppose that f is a positive continuous function defined on a finite interval, open bracket, a and b close, but has a vertical asymptote at b. Let big S be the unbounded region under the graph of f and above the x-axis between a and b. For type 1 integrals, the regions extended indefinitely in a horizontal direction. Here the region is infinite in a vertical direction. The area of the part of big S between A and T. The shaded region in figure 7 is big A of T equals the integral from A to T of f of x dx. If it happens that big A to the power T approaches a definite number big A as T approaches b to the power negative, then we say that the area of the region big S is big A, and we write the integral from a to b of f of x dx equals the limit as t approaches b to the power negative on the integral from a to t of f of x dx. We use this equation to define an improper integral of type 2 even when f is not a positive function, no matter what type of discontinuity f has at b. Parts B and C of definition 3 is sidebar. Parts B and C of definition B are illustrated in figures 8 and 9 for the case where f of x is greater than or equal to 0 and f has vertical asymptotes at A and C respectively. Figure 8, figure 9. Figure 8 has the vertical asymptote A. There's the interval from T to B on the x-axis. In figure 9, there's an interval from A to B on the x-axis with the C vertical asymptote. Back to the text. Definition 3 of an improper integral of type 2. Part A, if f is continuous on open bracket A and B close and is discontinuous at B, then the integral from A to B of f of x dx equals the limit as t approaches b to the power negative on the integral from a to t of f of x dx. If this limit exists as a finite number, part B, if f is continuous on open A and B close bracket and is discontinuous at A, then the integral from A to B of f of x dx equals the limit as t approaches A to the power positive on the integral from t to b of f of x dx if this limit exists as a finite number. The improper integral from a to b of f of x dx is called convergent if the corresponding limit exists, and a divergent if the limit does not exist. Part C, if f has a discontinuity at C, where a is less than c and c is less than b, and both the integral from a to c of f of x dx and the integral from c to b of f of x dx are convergent, then we define the integral from a to b of f of x dx equals the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Example 5. Find the integral from 2 to 5 of 1 over the square root of x minus 2 dx. Solution. We note first that the given integral is improper because f of x equals 1 over the square root of x minus 2 has the vertical asymptote x equals 2, since the infinite discontinuity occurs at the left endpoint of open bracket 2 and 5 close bracket. We use part B of definition 3 the integral from 2 to 5 of dx over the square root of x minus 2 equals the limit as t approaches to positive, or to the power positive, however you want to read that, on the integral from t to 5 of dx over the square root of x minus 2 equals the limit as t approaches to the power positive time of 2 times the square root of x squared, of x minus 2 on the interval from t to 5. Redoing that equals the limit as t approaches 2 to the power positive of 2 the square root of x minus 2 on the interval from t to 5 equals the limit as t approaches to the power positive of 2 open the square root of 3 minus the square root of t minus 2 close equals 2 times the square root of 3. Thus the given improper integral is convergent, and since the integrand is positive, we can interpret the value of the integral as the area of the shaded region in figure 10. Sidebar figure 10. The graph y equals 1 over the square root of x minus 2. The area equals 2 times the square root of 3.